Let's talk about sampling theorem. We will first talk about the intuition behind the sampling theorem, and then we will discuss the statement of the theorem itself. When we were discussing about discrete sinusoids, we saw that when we add 1 to a discrete frequency, we get back the same signal. In fact, adding any integer to a frequency will get back the same signal. When you look at the set of all discrete frequencies, the interval from minus 0.5 to 0.5 captures all possible frequencies. What this means is any other interval, for example 0.5 to 1.5, will result in frequencies, or the frequencies in 0.5 to 1.5 will result in the same sinusoid as in minus 0.5 to 0.5. Right? That means if we consider the discrete frequencies in the interval minus 0.5 to 0.5, we can generate all possible discrete sinusoids. Therefore, we will consider the range of frequencies from minus 0.5 to 0.5 as a standard discrete frequency range. Note that any two discrete frequencies within this range will generate different sinusoids. Now let's look at the sampling process. If you have a continuous time sinusoid cosine 2 pi fn t plus v, and your sampling rate is fs, then the discrete signal resulting would be cosine 2 pi capital F1 over fsn plus v. This means the discrete frequency is related to the continuous frequency using this relationship here. Therefore, the continuous frequencies in the range minus fs over 2 to fs over 2 are mapped to the standard discrete frequency range of minus 0.5 to 0.5. From the above discussion, we can say the following. Whenever the continuous frequency f1 is within the interval minus fs over 2 to fs over 2, where fs is a sampling rate, it can be accurately recovered from its samples because the resulting discrete frequency will be in the standard range, and we know how to map from the standard range back to continuous frequencies in minus fs over 2 to fs over 2. In other words, if you have a continuous sinusoid with frequency capital F1 and you sample it, you get a discrete sinusoid with discrete frequency capital F1 over fs, which is f1, small f1 here. So if you want to go back from your samples to the continuous frequency, all you need to do is multiply the discrete frequency with the sampling rate, and that will be your corresponding continuous frequency. Let's look at an example. If you have a sinusoidal signal with continuous frequency 100 and the sampling rate is 300 samples per second, then if you sample it, then the discrete frequency would be capital F1 divided by Fs, which results in 1/3. When you want to recover the continuous signal from the samples, you multiply the discrete frequency with sampling rate, which will give you back the continuous frequency. Now let's consider a continuous frequency continuous sinusoid where the continuous frequency is not in the range of minus fs over 2 to fs over 2, right? So here my 200 hertz is greater than fs over 2, which is 150 hertz of 150 samples per second. So when you convert this into discrete frequency, you use the same formula again, and you get the discrete frequency of 2/3. Note that 2/3 is not in the standard range of discrete frequencies. But we can convert this sinusoid or this frequency here into the standard range by subtracting 1 to 2 over 3, and we get minus 1/3. Note that if you subtract 1 from a discrete frequency, you get the same sinusoid. So these two signals are equal, right? So now minus 1/3 is in the standard range. Okay, so now if you and if you're just looking at the samples, you cannot distinguish between minus 1/3 and 2/3 because they will be the exact same samples. So now if you convert this signal back into continuous, the formula we are using is the continuous frequency should be the discrete frequency times the sampling rate, which will give us minus 100, and this is the signal we get back. So note that we started from this signal here, and we took the samples, we convert them back to continuous, and we got a different signal. So what this means is if you're using this process of going from discrete frequencies to come back to continuous frequencies by doing the inverse map within the standard range, if you're using that process, then what we just saw is whenever your continuous frequency is within this interval, it can be accurately recovered from its samples. And when it is not, you cannot recover it from its samples. What we have right now is a good intuition of when we can recover the original signal versus when we cannot. So let's now move towards writing the sampling theorem statement. Let's introduce the notion of bandwidth of a signal x of t. Let's say you have any continuous signal x of t. Note that we're not restricting ourselves to sinusoids anymore. This can be any continuous signal x of t. When you take the Fourier transform, you get capital X of f. Then the bandwidth of the signal is defined as the smallest frequency capital B such that x of f is 0 whenever f is greater than b. So in a way, this is giving us basically the frequency ranges or the range of frequencies in this signal x of t. To be consistent with the notation we're using, I converted all small f's into capital F's because all f's here are continuous frequencies. Based on our discussion above, we can say that when we have a continuous frequency, a continuous signal whose bandwidth is capital B, if you sample that signal and you look at the Fourier transform in the discrete domain, which is x of f, then the bandwidth of the discrete signal will be capital B over Fs. Now that B will map to capital B over Fs and minus B will map to minus B over Fs. So if the bandwidth in the continuous domain is B, the bandwidth in the discrete domain will be B over Fs. Also based on our discussion, we can say that if capital B over Fs is less than 0.5, that means this point here is less than 0.5, then we can accurately recover the signal. Also, if B over Fs is greater than 0.5, then we cannot accurately recover the signal. When this happens, this effect is called aliasing. And we saw this in this example here. When the continuous frequency was less than, in fact, in this case, 100 is also the bandwidth. When that was less than Fs over 2, we were able to accurately recover the signal. But if the bandwidth was greater than Fs over 2, we were not able to recover the signal. Okay, so this basically brings us to, this is basically what the sampling theorem says, and then I'll write the statement now. If the sampling rate is greater than twice the bandwidth, then the signal x of t can be accurately recovered from its samples x of n. In fact, the theorem also tells us how to exactly recover x of t from its samples. And this is the formula to recover it. So if you're seeing here, so you're considering x of n, x of t is a continuous signal from minus infinity to infinity, which means the samples x of n will also be from minus infinity to infinity. And the function g here is a sinc function. Okay, so let's focus on g of t as a function. So g of t minus nts, n or n over fs, would be the function g shifted to the right by n divided by fs. Okay, and then you're weighting that shifted signal for each n. You're shifting the signal by n over fs to the right, and you're multiplying that signal with x of n, right? So for each n, you have this shifted and weighted signal. You're adding up all those shifted and weighted signals to get back x of t. So that's what the sampling theorem says. Let's look at an example. Here is a continuous time signal with time on the x-axis and the signal value on the y-axis. Here is the same signals, but this time the sample values are superimposed on top of the continuous time signal. And in this case, I made sure that the sampling rate is slightly over 2.2 times the bandwidth. And 2 times the bandwidth is called the Nyquist rate. So my sampling rate is slightly bigger than what it should be in order to recover the signal perfectly. Now let's look at the process of recovering the continuous time signals from the samples. This is the stem plot of just the samples. As you can see, this would be sample for n equal to 0, or x of n for n equal to 0, n equal to 1, n equal to 2, 3, 4, and so on. The x-axis is still written in continuous time. So that means the x value here, let's say for n equal to 2, the x value will be the time corresponding to that sample, right? So that the x-axis here corresponds to the exact same x-axis here in the continuous time signal. Okay, and here it's just I'm plotting the samples themselves. So here I'm plotting the first few sinc functions, right? So know that the sampling theorem says when you're recovering the signal, so for each n, you take the sinc function here, you shift it by n times ts or n over fs, and then you multiply that by the sample value. And you take all these shifted and weighted sinc function and add them to get x of t. So here I'm plotting the first few, in fact, first 5 or first 6 sinc functions like n equal to 0, 1, 2, 3, 4, and 5, right? So that's the fifth, that's a sixth sample or x of 5. And I am taking g of t and it's shifted. So this x value is 5 times ts. So it's shifted to the right by 5 times ts. And then as you can see, its height is equal to x of 5. So I'm multiplying that shifted signal with x of 5, right? So again, so this sinc function here, or this signal here, would be x of 4 times g of t minus 4 times ts, and so on. So I can take, similarly for each sample, I will calculate a sinc function and plot the sinc functions for all the samples next. So here are all the shifted and weighted sinc functions. Now the sampling theorem says that if you add up all these signals, you should get back the original continuous time signal here in this figure, right? So if you add up all these sinc functions, you should get back the original continuous time signal. So here is the original and the recovered signal superimposed on each other. And you can see that the recovered signal is pretty close, except near the boundaries, which is a very complicated reason why it's not close over there. But except for the boundaries, you can see the recovered signal is pretty close to the original continuous time signal, right? So in fact, the recovered signal is basically the sum of all these sinc functions. So if you add up all these sinc functions, you get back exactly the original signal. Just to comment a bit more on what's happening here, let's see. So if you just look at this stem plot here, so you have sample values which you sample from the original signal, right? So what we want to do on this is these sample values are only telling us values at specific time points, right? So discrete time points, we know what the value of the signal is. So if we want to get back the original signal, we have to interpolate these samples to get back the original signal. And then we do this complex interpolation here to get back the signal which looks like the original signal, right? So the sampling theorem is basically therefore telling us what is the ideal interpolation is from samples, okay? And in general, adding all the sinc functions, okay, in general, adding all the sinc functions, if these are all the sinc functions, adding all of them to get back your original signal is a very computationally expensive process. So in order to it's a very computationally expensive process. So therefore, in general, this is not how standard interpolation algorithms work, and we have more computationally efficient interpolations. But they don't recover the signal exactly, but they come pretty close to, right? So the sampling theorem tells us what is the ideal interpolation is.